von Nobel, and he will tell us about Floquet-Bloch Theory and positive characteristics.
So I will start with a small preface, which is just recalling of my talk 2 years ago on this conference, and this will be a follow-up talk, or rather a lecture than a talk, because it will not contain serious results but some explanation of things. So that was the 2 years ago lecture was devoted to such a game which is industrialized. You can buy it and play, and this consists in the following. You have a board, rectangular board with the sizes, and in each square, small square, you have a coin which have two sides, black and white or 0, 1, and therefore you have some initial position of 0, 1s everywhere. And the move consists of reversing the coin together with its immediate neighbors. And after a sequence of move, you have to reach the white position, the 0 position, all zeros. So the board is winning if it is possible. So the winning strategy exists for any initial position. And then for some m and n it is winning, for others it is not winning. So the answer for which precisely pairs m and n it is winning is unknown. So the content of my previous talk was a criterion formulated in terms of harmonic functions. So the board is winning if and only if there is no harmonic function on it. So harmonic I will put in the geomap because I have to explain the functions considered are 0, 1 functions with two values, and harmonicity under this circumstance means that the sum of values over a star means the central square, and for neighbors is 0, always 0. This is harmonic function. Then we can transform this problem a little bit to manage easily with it. And the first transformation consists to suppose the periodicity condition, the boundary condition. That means that the value on the left upper line and lower line and left column and right column are so the same, so that you can glue this rectangular board into the finite toric board. The second step consists to come to the cover by the lattice. So the finite torus is covered by the lattice z square in the plane, which I will denote by lambda. And so the function downstairs lifts to the function which is double periodic. So the period m in one side, in one direction, and n in another direction, and the Laplacian which you apply so to define harmonicity became a Laplacian upstairs. So the harmonic functions give the harmonic functions upstairs, and you wonder for which periods, couple of periods, pair of periods, you do have the double periodic harmonic function with 0, 1 values. And this is really the problem. I explained the last time that the difficulty probably is very essential because it's is related somehow to hard number theoretic problems. For instance, the so-called Artin problem on primitive roots. Therefore, I don't know whether it's hopeless, but at least it is difficult. And now, after my talk, Peter Kuchman realized that a part of technique that participated in the proofs was well known to him, and in the brackets of the version of Floquet theory that some 20 years ago he put it into this frame of discrete setting, so for difference operators on graphs. So I would like to say that you can plate this on arbitrary graph, not necessarily graph which is of this type, and then your move is to switch 0 to 1, 1 to 0 on one vertex and on all neighbors of this vertex, and then you have the same aim. So then what can be done? You can consider now the maximal abelian cover of your finite graph where you're playing this game. Maximal abelian cover is an infinite graph, so-called. This was also, this notion appeared in the probably another framework of the work of Professor Sunada and his collaborators. And so you come from this gamma to say gamma tilde, which is not which is not universal cover, but which is cover such that the homology group of gamma, not fundamental, but the homology group, which is free abelian group, acts here, and this homology group will be lambda. It acts freely on this infinite graph, and the quotient is our original gamma. Then the function of gamma on gamma so leads to a periodic function on gamma tilde, and so you can apply Laplacian on gamma tilde and so on, and you can play this game on gamma tilde and interested in periodic solutions. Then it's natural then to forget the original graph totally, because once the operator is given, the Laplacian is written, it carries information about the graph. Therefore, instead of thinking about the vertices and so on, you can replace this gamma tilde just by a set of vertices. So, and then you have a fundamental domain on this graph, some finite subset of vertices, such that the translations of this finite subset covers without intersection the whole gamma tilde. And then the function on gamma tilde becomes, so you consider the restriction to a fundamental domain just as a vector of length equals to the number of vertices in this fundamental domain. And then you have a finite dimensional vector space, and instead of scalar functions, you're now dealing with the vector functions, and I call this process fragmentation. From scalar function to vector functions, you make the fragmentation, and your Laplacian is now the matrix operator on this space of vector functions. So this is just what people are doing. So the periodic graph appeared already in 70s in the papers of Kollatz, and then probably a list of names. And so Floquet theory was done as a Floquet theory properly by Peter Kuchman. So this is everything was in the paper of Kuchman. The only difference that he was working over real, so complex, and I'm working in positive characteristic, which makes a difference. And so my aim is to explain this difference. So on one side, the positive characteristic is simplifying, and I explain why and where it is simplifying things. On the other hand, the p, which is a characteristic, p is a prime integer, which we fix, it intervenes into the theorems, even into the objects. It plays essential role. And this is really, really should be like that, because the answer for the game, say, depends on P. The boat which is winning for one P is not winning for another P, and so on. The set of winning boats of these pairs, M and N, depends on P in a very essential way. Therefore, it's not surprising that P changes the setting. So now the field, the principal field will be the finite Galois field of characteristic P, which is a minimal field of such type. And then we will work first in its algebraic closure. To the end, I will come to the original field. So the algebraic closure, which is denoted by K capital, has such a property that its multiplicative group is relatively simple. And this is a major difference. That means that every element, non-zero element, has finite order, finite multiplicative order. And every finite subgroup is just a cyclic group. And every cyclic group is isomorphic to the group of roots of unity of this degree, of this multiplicative, of this field. Okay, so now what we need also, we need the dual group lambda check, which is the group of characters but with values, so in this multiplicative group K star. And this is a torus, so once you fix a base of your lattice, it became, so lambda becomes isomorphic to z to the power s. S is a rank. And then the dual group becomes isomorphic to the what I call torus of dimension s, which is by definition just the multiplicative group to the power s. So algebraic torus. Okay, and now we have to define the Fourier transform. Our aim to define the Fourier transform, which transform functions on lattice, on the lattice to the functions on the torus. Which kind of functions I will explain. Okay. So to go further, I will just show the main features of this couple of papers of Kuchment, and then some subsequent papers of himself and collaborators will appear later on. So that that is a theorem. So we have a periodic graph gamma with a lattice which acts freely on it with finite number of orbits. Then and we have a periodic difference operator on functions on gamma. Then you can find always a special so-called Floquet solutions, a sequence of these solutions, such that any solution is a series, convergent series of this sequence with constant coefficients. Then every L2 solution is approximated by solutions with finite support. Therefore, you have L2 solution if and only if you have a solution with finite support. And finally, there is a criterion that I will not formulate when there exists a solution with finite support. So, of course, the convergence will not participate in my talk, just algebraic setting, linear algebra, nothing else. And nevertheless, I will mention some analogs of these results. So now let us define, as usual, the convolution operator. For this, we consider K of lambda, the group algebra of lambda over K, consisting of all functions with finite support, and multiplication is a convolution. So then we can fix one factor and get running the second one. So A will be so-called kernel of the convolution operator, A small, and F will be the argument. And then we have a convolution operator. So kernel is exploited in two senses, as this nucleus or this A, and also as a zero subspace, which consists, we will call delta harmonic functions. So now we introduce, as usual, the delta functions, and we remark that if you convolute with delta, this is a shift, and any convolution operator is just a linear combination of shifts, as usual. Therefore, it commutes with shifts, and any operator commuting with shifts is a convolution operator. Now, so when the kernel A small is with finite support, then you can apply the convolution to any function, arbitrary function. So the space of all functions will be F round, and then it acts automatically on any translation invariant subspaces, and I will mention some of these translation invariant subspaces, 5 of them. And so first of all, there is this group algebra which consists of functions with finite supports, translation invariant. Then if you fix a period lattice, some sublattice of your original lattice, lambda prime, then you can consider functions which are invariant by shifts by vectors in lambda prime. That means that the period lattice of such a function f, which I denote lambda of f, contains this lambda prime. And this is not translation invariant, only translation invariant by lambda prime. Then the first important subspace is the subspace of traces of polynomials. It is translation invariant because the characteristic is positive. So when I say polynomial, I identify my lattice in some way with the integer lattice in so the affine space, and then the polynomial is defined on the ambient space and restricted to the lattice. Then you can consider all pluriperiodic functions, means the union of functions as in the second item over all sublattices of finite index. So the function is pluriperiodic if its period lattice is of complete rank, but the index can be arbitrary finite index. Okay, then it is definitely translation invariant. Then the E3 is polynomially periodic functions. What does it mean? That means that you take for any function in this space, there exists a sublattice of finite index and a number of polynomials, fixed polynomials, finite set of fixed polynomials corresponding uniquely to the conjugacy classes by this sublattice. And then the restriction to each conjugacy classes is a trace of corresponding polynomial. This is polynomially periodic functions. Then the next class E4, so-called Floquet functions. They are linear combinations of the products of characters. Chi I is a character, and Gi is polynomially periodic. So finite linear combinations. Also, characters are translation invariants, and so these combinations as well. Then the last space will be lambda prime automorphic, where lambda prime runs over finite index sublattices, and then the automorphicity means that when you shift by the element of lambda prime, which is small u, then your function is multiplied by a value of certain character on this u. And then the simplification of the positive characteristic consists that among these 5 spaces that in 0 characteristic are all different, there are only 2 different in positive characteristic, the first one and all the other coincide. So the traces of polynomials is smaller subspace, and all multiperiodic functions is a bigger one. So this is a simple result, but somehow it shows something. Now we will introduce a new space which was not in the list, which consists also in multi-periodic or pluriperiodic functions, but with some restrictions on the lattice of period. And the restriction is, so it is given in this definition. So a sublattice of finite things lambda prime is p-saturated if its index is co-prime to p. That means that the quotient group has no p torsion. So there is a possibility to divide by p. That means that if p times a vector is in lambda prime, then the vector itself should be in lambda prime. And this is somehow a restriction of the class of sublattices that we are dealing with, depending essentially on p. You change p, you change the class of sublattices. And the class of functions that participate. This is a vector space of function which is translation invariant. Then, so actually the space will consist of the span of characters, just the linear span of all characters. And the proposition says that this definition gives actually a characterization of such functions. So if you consider the space of all functions such that the pluriperiodic and the period lattice is p-saturated, then this is exactly the space of all linear combinations of characters. And this is appropriate space to define the Fourier transform. So the Fourier transform, I will give two definitions. First for functions with finite support, and second for these functions in Fp, pluriperiodic. So the first is very simple and usual. So you consider the space of regular functions O of lambda prime on the torus, on the dual torus. Then the elements of this space are just the Laurent polynomials in S variables, once you identify the dual torus as the standard torus. And then your function f, which was a finite support function on the lattice, gives you the coefficients of this Laurent polynomial. This is exactly the Fourier transform. Therefore, the delta functions goes to a monomial, corresponding monomial, nothing else. Monomial in S variables, and Laurent monomial, where the exponents can be positive or negative. So this means that the convolution of delta functions gives you the product of monomials as should be. Okay, and the inverse consists to so may correspond to a Laurent polynomial, its coefficient function, which is of finite support. Now I'm coming to the second setting when you are dealing with functions, pluriperiodic functions, not with finite support. And how to define the Fourier transform. So I have to introduce the space of functions on the dual torus which have finite support, functions with finite support. And then the definition is extremely simple. So the definition is the following, that you send the space of Fp, which I defined before, on lambda to the space of function with finite support on the dual torus, making corresponding to a linear combination of characters, the function sitting on these characters, but you have to inverse the character. So I mean that the support will be just this set of characters. Characters are the members of this torus, the points in the torus. Okay, so the inverse, if you have a finite supported function on the torus, you just write the corresponding linear combination of characters with inversion, and then you have the inverse of to the Fourier transform. And the main feature that is preserved under all these formulas is that, as usual, it should be the Fourier transform of the convolution is the product of the Fourier transforms, and this is very simple. Now let us come to the equations. So we have a convolution operator, and we have to consider so harmonic functions, which are the function vanishing under the convolution with A, which is finite supported. And then we have to define the set of solutions, and this is now easy. So we consider the Fourier transform A hat of the kernel A. This is a Laurent polynomial. We associated to this Laurent polynomial, which is a regular function on the torus, on the dual torus, its zero set, which is a algebraic hypersurface, a fine hypersurface in this torus. And then this is called a symbolic variety. Now, the points of the dual torus are characters. The character is delta harmonic if and only if it is sitting in the symbolic variety. So the symbolic variety is a set of harmonic characters. That's all for a given convolution operator. So then the proposition says that it's immediate from this description that a non-zero harmonic function cannot have finite support. Then the point B, that every harmonic function is a linear combination of harmonic characters. And that means that if you know the symbolic variety, you know the kernel of your convolution operator. And the immediate corollary, the inversibility of such an operator almost never happens. This corresponds to the empty symbolic variety, and this corresponds just to the shift up to a constant factor. Nothing else can be inversible. And this is also more or less evident. Now let us deal with more general spectral analysis, which is also quite easy in this setting. So this is concerned Floquet-Fermi hypersurfaces, which were employed in the paper of Couchement and Weinberg. So we still have a convolution operator acting on scalar functions. We are interested in pluriperiodic solutions. And then we introduce, for given scalar mu, we introduce the analog of symbolic variety, which is mu level of this Laurent polynomial with inversion inside. And this is called Floquet-Fermi hypersurface. Also, we take the characters sitting on this hypersurface and the span, linear span of these characters. The characters are, as usual, orthogonal. Therefore, these linear spans don't intersect for different mu and mutually transversal. And this is an eigenspace with eigenvalue mu. And then the proposition says that the whole space of pluriperiodic functions is a direct sum of these eigenspaces for all mu. And this means that the convolution operator can be diagonalized in the basis of characters. And so, I mean, all these results are very easy results, evident. And this is more evident when I would say that the Fourier transform sends the convolution operator to the operator of multiplication by the Fourier transform of the kernel, by this Laurent polynomial. But the multiplication operator is, of course, semi-simple. Therefore, the convolution is also semi-simple. And the spectrum is also, the spectrum is appears immediately. Then I come to this more general setting when you are dealing with vector functions, which comes from this construction, which arises from this construction. And I introduce the notation, the affine space over K with canonical basis, then the functions with value, vector functions on this, vector functions with finite support, and vector functions such that each so element of this vector function is a function from Fp. Then what is important for us, this is a analog of delta functions or Bloch functions, which will be elementary vector functions, just a constant vector multiplied by a monomial. Monomial considered as a character of lambda. Now the operators. So we consider endomorphisms of this space of vector functions which commute with shifts on vectors of lambda. So then to define uniquely such an endomorphism, it's enough to consider the delta functions sitting at 0. So in 0 you have the vector space sitting in the 0 of the lattice, in the origin of the lattice, and then you have n basic vectors, and each of these vectors is considered as such a delta functions, delta I0 written upstairs. And then if I know the values of my endomorphism commuting with shifts on these vectors, it's enough to reconstruct the whole endomorphism, because these values is a string of functions with finite support. Then, because I'm taking n such values, then I have a matrix A capital of such functions with finite support on lambda. And then if I would like to know the value on any other elementary function, then I just apply a shift to these values on the 0. And therefore, because it's commuting with shifts, therefore this matrix knows everything about our endomorphism, our operator, and it acts now, the operator acts as it follows. I take a vector functions f with scalar functions f of f1, fn, and the value g on this delta of f consists of components gi, which are computed by this simple formula. Then, so this is the matrix convolution operator, well known in 0 characteristic at least. And the theorem, which is also no surprise, says the following. So take such a matrix convolution operator or endomorphism commuting with shifts and consider the equations delta f equals 0, then non-zero solution, and this is a point of Cushman's paper as well for 0 characteristic, and it holds as well with the same proof in positive characteristic. Non-zero solution appears if and only if the determinant is identically 0, a 0 Laurent polynomial. So the determinant is taken of the Fourier transform of our matrix, which is a matrix of Laurent polynomials. Now, now take a sublattice lambda prime, and we are interested in lambda prime periodic solution. We assume that the index is coprime to P, so P saturated sublattice. Then F is a solution if and only if, so there exists a solution F, non-zero solution F, if and only if there exists a character chi such that the determinant is 0 on this character, and also the kernel of this character contains our sublattice lambda prime. So those characters that are orthogonal to lambda prime form a finite subtorus in our torus. So the torus T to the power S is and infinite torus, but inside their torsion subtori, it is filled in by the finite subtori. And so we have to take, if we would like, we have to take this orthogonal subtorus, finite subtorus, and the determinant should vanish in some point of it. Then we can find such a solution. And even we can find an elementary solution, which means the solution of type vector times character. So then this gives a description as a span for all the kernel. Of course, this description should involve the notion of symbolic hypersurface. This time, this hypersurface is determined through determinant, which is a Laurent polynomial, the determinant of the Fourier transform of our matrix, the symbolic variety. Then there is a terminology multipliers for these points sitting on this variety. And then we can rewrite lambda periodic solutions as a finite combinations, because you take the symbolic variety intersecting with a finite subtorus. And then if you have, and U is sitting for every fixed value of Z, so you have a scalar matrix, you have a kernel, and U is a vector from this kernel. This gives a complete description of the kernel, and the same, of course, you can get for the proper subspaces. So then the corollary is that a non-zero solution exists if and only if there exists an elementary non-zero solution. Okay. So, of course, when the matrix appear on vector functions, then of course you are not anymore in the setting of semi-simple, as in the scalar case, but nevertheless you have a Jordan form. So you know that over any algebraically closed field, a matrix admits a Jordan form, Jordan basis, and the same in our setting, any such a endomorphism commuting with shifts also admits a Jordan basis. For this, we're following so Couchement-Weinberg, we introduce the Floquet-Fermi level in the same way as for scalar, but using the determinant this time. And for instead of eigenspace, it's worthwhile to consider generalized eigenspace, which means that to take kernel of the nth power of this shift of our operator. Then the theorem says that the whole space is the direct sum of this generalized eigenspace. Given such a matrix convolution operator, so the space of periodic vector functions, pluriperiodic, is the direct sum of proper generalized eigenspaces, and they are generated by elementary vector functions. So I stop here. So that means that monomial times fixed vector, where the vector is taken for this character from the kernel of this. So there is a Jordan form. And now I'm passing to the finite field case. What can be said in the finite field case? So usually, for instance, if you are coming from this setting, then you are interested in functions taking value not in the algebraic closure, but in the original field. And that means that you consider the matrix convolution operator where the entries are the members of the finite field. And you are asking about solutions in the same finite field. Now, you cannot expect the orthogonal basis of characters anymore, because characters are not, of course, are not taking values in a finite field. They are taking values in the algebraic closure. But what can be done? You can apply somehow suitable trace. So in the number theory for field extensions, you have a trace which is a homomorphism from bigger field to a smaller field, and this trace is allowed you from any solution defined over the algebraic closure get a solution, because taking trace preserve harmonicity and periodicity. Then you get a solution in the original field, which are not, these new solutions are not orthogonal, are not anymore linearly independent, but nevertheless span the whole space. And as a result, you can, the theorem says that so if there is a non-zero solution in the algebraic closure, then there is another non-zero solution, non-zero again, with values in the finite field. So, okay, you don't have the elegant description, but nevertheless, you have solutions. So now I'm coming to the last part of my talk. I have a few minutes to examples, and so now this is the fragmentation is something that I explained already. I will not stay on this. So the toy model for fragmentation is a model when you don't start like here from the finite graph or whatever, but you consider a lattice and a sublattice, but you consider the action of sublattice on the lattice. You shift only on the element of sublattice. In this case, any scalar function on the bigger lattice became a vector function on a smaller lattice. And the operator which commutes with shifts by a smaller lattice became a convolution operator on the bigger lattice, a matrix convolution operator. And then the question arises how they related these two operators, the original one and the new one. And of course, they are related in the good way, so there is no surprises. So, for instance, consider just the shift by 1 on the lattice of rank 1, just Z, and as a sublattice, you consider n times Z. Then you have n, so the vector functions on the new lattice, on the sublattice. So instead of scalar functions with the values in the an. And then it can be, the original can be diagonalized in the basis of character, and the second one can be diagonalized in the basis of elementary functions. The matrix, to visualize the matrix that appears here for this shift operator, it is this vector. Actually, this is not only Laurent, but just monomial, polynomial. So in Z, matrix which is polynomial in Z, this corresponds of order n. And then you can describe in a very simple manner the symbolic hypersurface, which consists of just nth root of unity in this case. You can describe also very simply the proper vectors, and then you can resolve your situation completely. And the conclusion is that isomorphism of fragmentation in this case sends the basis of characters in the original lattice Z capital to a basis of elementary functions, which is diagonalizing for fragmentation of our operator. And the last example, the very last example, is example when the lattice is of rank 2, and you consider two operators. So the lattice, so the bigger lattice is Z2, Z square, and the smaller lattice is 2 times Z times 2 times Z of index 4. And the characteristic is different from 2 in order that it would be p-saturated. And then you consider the shifts tau 1 and tau 2 in 2 directions in the standard basis. The matrices which are Fourier transform, so Laurent polynomial matrices, are now this A1 and A2. then you can choose a common basis of eigenvectors for these two matrices, where x and y are chosen so that x square is z1 and y square is z2. So then you can consider now more general setting. You take a Laurent polynomial of two variables, z1 and z2, and then you apply this phi Laurent polynomial to tau 1 and tau 2. Then you get a completely general convolution operator on z square, and you fragmentate it, and you are interested in the basis, but the basis appears also immediately. So you can consider these four functions produced by changing signs of variables. So, and then you have that applying Q operator to elementary functions gives a multiplication by such a function of this elementary function. Then you have proper values, and you have the description of Fermi, Floquet-Fermi level mu sets, explicit as the level sets of these Laurent polynomials in x and y, and then you have the direct sum decomposition. In this case, this is not generalized, but just proper subspaces, and the final sheet of formulas is this one. So you have the description of eigenspaces through elementary solutions. Then for 0, you have the same description. And that's all. So these are very simple examples, but just to show what can happen. In conclusion, I am very sorry that this so simple and so nice presentation did not give any new results for the game. That was my aim. I hoped to get them, but so far there is nothing, no news. It's too simple. Okay, I finished.